This video is a 1-hour summary of all the topics in AQA AS-level Chemistry Paper 1. So that's all of the physical chemistry apart from kinetics, and then all of the inorganic chemistry as well. The first topic in Year 12 physical chemistry is atomic structure, and a lot of this is very familiar from GCSE. You should know that an atom consists of a nucleus containing protons and neutrons, and we call those particles nucleons, and they're surrounded by electrons. The absolute masses and charges of the subatomic particles are incredibly small. Rather than referring to those actual numbers, we tend to talk in terms of atomic mass units and atomic charge units. An atomic mass unit is 1/12 of the mass of one atom of the carbon-12 isotope. You need to appreciate that knowledge and understanding of atomic structure has evolved over time. This hasn't come up a huge amount, but in 2018 we were asked about the differences between the modern model and Thomson's plum pudding model. You should be aware that the plum pudding model has no nucleus and the electrons are not in shells, they're just scattered throughout the atom. And then in 2021 we were asked about Rutherford's nuclear model. This doesn't include protons and neutrons, it just has one undifferentiated nucleus, and then the electrons are not separated out into different energy levels or shells, they all just orbit the nucleus together. We define an element based on the number of protons it has. Any atom with one proton is hydrogen, any atom with two protons is helium, and so on. The number of protons is called the atomic number, and this has the symbol Z because of the German word Zahl, meaning number. The sum of protons and neutrons in the nucleus of an atom is its mass number, and that's A. Mass number is always an integer because for one particular atom, the number of protons and neutrons is always going to be a whole number. For any species, you should be able to identify the number of each subatomic particle. This titanium ion, because it's titanium, must have 22 protons. Then, in order to work out the number of electrons, we look at the charge. Here it's 3+, so we're expecting 3 fewer electrons than protons, so that's 19. And then to work out the number of neutrons, we do the mass number, take away the number of protons, which gives us 26. Isotopes are different atoms of the same element, and therefore they have the same number of protons, but they have different numbers of neutrons. They're chemically identical, in other words they undergo exactly the same chemical reactions because they have the same electron configuration, but they're physically different because they have different numbers of neutrons, so they may have different melting points, radioactivities and densities. Unlike mass number, which is for one particular atom, relative atomic mass is a figure which takes into account all of the different isotopes of an element, whether that's in the whole world or just in a particular sample, and also their relative abundances. If we have a lot of a particular isotope, then it makes up a greater proportion of the relative atomic mass than a rarer isotope. We can define relative atomic mass as being the average mass of one atom of that element compared to 1/12 of the mass of one atom of carbon-12. You can also use the same definition, substituting the word mole instead of atom, as long as you're consistent with yourself. There are a few different types of relative atomic mass calculations, starting off with our vanilla GCSE calculate the relative atomic mass. So in order to do this, we're going to take the mass of each isotope and multiply it by the abundance of that isotope. And then we're going to divide our total by the total of the abundances. Now we're going to do a little common sense check. Is that answer between the masses of the isotopes and is it nearer to the more abundant isotope? Our second style of question is similar, but instead of percentage abundance data, we're going to have raw abundance data, which doesn't add up to 100. This means that whereas with the previous question I could have answered it by using decimals, here I need to do the full fraction, and I need to be aware that the denominator of my fraction here is going to be 32, not 100, and this is a really common mistake that we see people making. So I'm going to go through exactly the same process, and then I'm going to do that same common sense check. Is my answer between 14 and 15, and is it nearer to the more abundant isotope? Our third possibility is that rather than being given the isotopes and the abundances, we're given the relative atomic mass and asked to work backwards. So the first thing that we're going to do is to write an expression for what relative atomic mass is, substituting in the numbers that we've got. And here I'm using X as the mass of the isotope because I don't know what it is. So I can then solve that, and I'm going to get an answer for the mass of the missing isotope. Now in this instance I'm going to find out that I actually have an answer that is not a perfect integer. But remember, mass number has to be an integer, so it's really important that I'm rounding before giving my final answer. To generate the abundance data that allows us to calculate relative atomic mass, we need to use mass spec, and for AQA A-level chemistry all you need to know about is time of flight mass spectrometry, not any of the other versions. Mass spec is an analytical technique that allows us to measure the mass to charge ratio of ions, but since the vast majority of those ions are only going to have a single positive charge, this is really basically just giving us the mass. You need to be able to talk through the 5 steps of mass spec. The first step in mass spec is ionization, and depending on the kind of substance that you're trying to analyse, you might use one of 2 different methods. If we have a large molecule like a protein that could fragment easily, then we're more likely to use electrospray ionization. This is where the substance is dissolved in a volatile polar solvent like water or methanol, and then it's injected through a needle that's attached to a high voltage power supply. In that process, each molecule gains a proton, and this gives the final ion a positive charge and an atomic mass 1 unit heavier than the original molecule. Say if we were analysing decane, it's got an MR of 142, so the final ion would have an MR of 143. Alternatively, we can use electron impact ionisation, and this is where we use an electron gun to fire high energy electrons, and those electrons knock another electron off the original substance, and therefore the mass of that new ion is the same as the mass of the original species, but it has a positive charge. Next, all of those ions are going to be accelerated, and this is done by them being attracted to the negative plate, because of course they all have a positive charge. And then they're going to travel through the drift chamber, and that's how they all end up spreading out. And they're going to be detected when they hit the negative plate, and they pick up an electron, and this causes a current to flow. And then the size of this current is directly proportional to the abundance of that ion. If there are twice as many of the ion, we'll see twice as large a current flowing. It's very likely in a question on mass spec that you'll get 5 or so marks for a calculation where you need to work out something like the length of the flight tube, the time taken for an isotope to move, or the mass of a second isotope if you're given the first one. In these questions, they will give you the equation for kinetic energy that you used to have to memorise for GCSE, but they only give it to you in one form. So if you're not very good at rearranging under pressure, it's worth learning the rearranged version with V as the subject. Watch out for the fact that in order to be used in that calculation, the mass needs to be in kilograms, even though you're used to having masses in grams for masses Mr. Mole type calculations. And also be aware that you do need to learn how to calculate velocity, which is distance divided by time. Rather than using numerical data, you could be given a mass spec readout to interpret. Watch out that again this could be abundance values rather than relative abundance values, so they may not add up to 100. Atoms with more than one stable isotope can lead to some funky mass spec data in terms of their molecules. We know that 3/4 of all the chlorine in the world has a mass of 35 and the remaining quarter has a mass of 37. And we also know that chlorine exists as diatomic molecule, Cl2. So the chances that I have a chlorine molecule containing 2 atoms of chlorine 35 are 3/4 times 3/4, which is 9/16. And the chance that I have a molecule made of 2 chlorine 37s is 1/4 times 1/4, which is 1/16. And so the chance that I get a chlorine 35 chlorine 37 molecule is 6/16, and I get a 9:6:1 ratio of the molecules. Electrons occupy fixed energy levels, which we call shells, and the shells can be further divided into subshells called S, P, D and F, the same as the blocks of the periodic table. And each of those can be split up into 1 or more orbitals. An orbital is an area of space where there's a high chance of finding an electron, and all of the orbitals have room for 2 electrons in them. There's 1 s orbital per subshell, 3 p orbitals and 5 d orbitals, and in any given energy level the s orbitals are the lowest energy level. Later we encounter questions about how easy it is to lose electrons, and we always refer to the fact that a p orbital is higher energy than the s orbital. These orbitals also have characteristic shapes. S orbitals are spherical, the p orbitals are dumbbell in shape in 3 different orientations, and then the 5 d orbitals are a clover shape. There are 3 key principles for arranging electrons in atoms. We always work from the lowest energy to the highest energy. For instance, we always put things in S subshells before we put them in P subshells. The second rule is that within any particular orbital, 1 electron spins up and 1 electron spins down. And the third rule is that we don't start pairing electrons in orbitals as long as there are other orbitals free in the same energy level. We're going to put electrons into them separately, and then once they all contain 1 electron, then we can start pairing our first electron. Hydrogen is simple, and then in helium we pair up those electrons. We don't move on to the 2s subshell because it's higher energy, and therefore we're allowed to pair in the 1s subshell. Then in lithium we go 1 up, 1 down, and then we start the new subshell. In beryllium we again have to pair because the 2p orbitals are higher energy than 2s. Then with boron, we're allowed to start using that 2p subshell, and then when we get to carbon, we don't pair the 6th electron because there's still another orbital which is the same energy as the first 2p orbital. And then likewise, nitrogen, we're not pairing. It's only when we get to oxygen that we start to pair those electrons. There are a couple of little things that might trip you up. The first one is that despite being part of the 4th shell, the 4s orbital is lower energy than the 3d orbital, at least when it's empty, and therefore we put electrons in there before we put them into 3d. However, the presence of electrons in that orbital change its energy level, and that means although it's lower energy than 3d when it's empty and therefore it fills first, once it contains electrons it becomes higher energy than 3d and therefore it also empties first. If you're writing the electron configuration for a titanium atom, then we would have 4s2, 3d2. I'm just using the noble gas configuration here in order to save time. But then when it comes to a titanium 3+ ion, it's going to lose those 2 electrons out of 4s before it starts losing from 3d. It's still left with 1 in 3d. I wouldn't actually write 4s0, but I'm just putting it in so that you can see that they've been removed from there. The other rule that might trip you up is what I refer to as the copper and chromium rule, because these are the 2 elements that you're most likely to encounter it with. We know that atoms are more stable when either all of their d orbitals are full or all of their d orbitals are half full. In other words, having 3d5 or 3d10 is much more stable than 3d4 or 3d9. And therefore, when for instance we get to nickel, we would have 3d8 4s2 because that 4s is filled up first. But then when we get to copper, we take one of those electrons back from 4s and use it to top up the 3d, so that we actually get to 3d10 rather than 3d9. First ionization energy can be defined as the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms of that element to make 1 mole of gaseous ions. It's really important when you write an equation for this that you're including the state symbols. It's also worth emphasising that it doesn't matter what the element is. It doesn't matter if in chemical reactions it forms negative ions or 2+ ions. First ionization energy is always about removing 1 electron to make a single positive ion. You need to be able to explain why we see variation in first ionization energy across the periodic table. The first thing is that there's a general trend as you move from left to right and we see an increase in first ionization energy, and the reason for that is the increased nuclear charge. As we go left to right, each element gains 1 more proton, and therefore there's a stronger electrostatic force of attraction between the nucleus and the outer shell electrons, and that means it takes more energy in order to remove that 1 outer shell electron. The second thing we see is a drop in first ionization energy as we start either a new subshell or a new shell. And the reason for this is that these electrons are in higher energy subshells or shells, and therefore they're experiencing more shielding and they're further away from the nucleus, so they're more easily lost. The third thing we see is a drop for oxygen in period 2 and sulfur in period 3, because the electrons are now being paired in an orbital, and the paired electrons are repelling each other more strongly than unpaired electrons would do, and therefore that is decreasing the amount of energy needed to remove that electron. The amount of substance topic begins with the mole and the Avogadro constant. You should know that the Avogadro constant represents the number of particles in a mole, and that could be atoms, molecules, ions, electrons, literally any type of particle. In all your calculations, you need to give your answer to an appropriate number of significant figures, which is the smallest number of significant figures used in the question. At A level, we no longer talk about concentration in terms of grams per decimeter cubed, and we almost exclusively use moles per decimeter cubed, but you could still be given mass data and expected to use masses Mr. Mole to convert to moles in order to be able to calculate a concentration. The ideal gas equation is everybody's favourite because you can often pick up 2 marks just for recalling the equation and converting all of the numbers in the question to the correct units. So make sure that you're aware that pressure needs to be in pascals, so you're going to need to multiply it by 1,000 if it's given in kilopascals. Volume is in meters cubed, so you often need to multiply a value in centimeters cubed by 1,000,000, and temperature needs to be in Kelvin, so you may need to add 273 to a temperature that's been given to you in Celsius. Empirical formula is the simplest whole number ratio of atoms of each element in a compound. Ionic compounds have a formula that is already an empirical formula, but for a molecular substance it may or may not be the same thing. For instance, all alkenes have an empirical formula of CH2. To calculate empirical formula from mass data, we're going to start off by using masses Mr. Mole to work out how many moles of each element we have. You rearrange the equation, and then we work out that we've got 0.3 moles of nitrogen and 0.6 moles of oxygen. Then we put those together in a ratio, and we need to convert this to the simplest whole number ratio, which we do by dividing by the smaller of the 2 numbers. I divide the left side by 0.3 and then the right side. Don't fall into the trap of dividing both sides by themselves, because then you'll just get a 1-to-1 ratio. This gives me an answer of 1 to 2, and then I need to express my answer as an actual molecular formula, which here is going to be NO2. To balance equations, start off by writing down the number of atoms of each element on each side. Then look for an element that's not balanced and think about what the lowest common multiple would be. Here I'm going to start with carbon, and the lowest common multiple of 1 and 7 is 7. So I need to multiply by adding coefficients, and here I'm going to add a 7 in front of the carbon dioxide. Next I'm going to think about the hydrogen, and here I'm trying to balance 6 versus 2. So the lowest common multiple is 6, and therefore I need to add a coefficient of 3 on the right hand side. Then I'm going to think about oxygen, and I've got 17 in total on the right hand side. So I need 17 on the left hand side, but I also need to take account of the 2 that are in the carboxylic acid. Once I remove those, I'm left with 15, and therefore I need to add 7.5 as a coefficient for the oxygen. Start answering a theoretical yield question by doing your housekeeping and removing anything that's not part of the question, and then writing down the MR of the other substances. Use mass is Mr. Mole to work out what the number of moles is of the substance that you do have the mass for. So here I'm going to find that I have 0.5 moles of sodium azide. Then I need to look at the coefficients to work out how many moles I have of the second substance, and this is probably the most common thing that students leave out when they're doing these calculations. You divide by the coefficient of the thing you already know about and multiply by the coefficient of the thing you're trying to work out. So I've got 0.75 moles of nitrogen. I then go back to mass is Mr. Mole to work out that I've got 21 grams. Atom economy is a measure of what proportion of the reactants I started with actually ended up in my useful product, as opposed to in a byproduct that I can't use. Having a reaction with high atom economy is desirable because it's going to save me money. It's going to mean that resources are better preserved, and it's probably going to save energy as well and generally be better for the environment. It's highly likely that you'll be asked to write a balanced symbol equation for something where you haven't been given the formula of all of the compounds. Now, from GCSE, you should be familiar with how to work out the charge on a monatomic ion based on which group it's from, but then you're also expected to recall some compound ions, both what their formula is and also what the charge on them is. That's ammonium ions, sulfate, carbonate, nitrate, and hydroxide. Phosphate isn't actually on the list of ones you're expected to recall, but particularly if you have reactions with phosphoric acid, it's useful for you to know that it exists and also that it has a 3- charge. If we're making an overall compound, it needs to have no overall charge. So to balance the positive and negative charges, look for the lowest common multiple. For aluminium sulfate, the lowest common multiple of the 3+ and the 2- is going to be 6. So to get 6 positives and 6 negatives, we're going to need 2 aluminium ions and 3 sulfate ions. And remember to use brackets around your compound ions in the final formula. In addition to balanced symbol equations, you may be asked to write ionic equations and half equations. We'll look at half equations in more detail when we get to the redox topic, but remember that for an ionic equation, you want to start out with your symbol equation, take any ionic substances and break them down into the ions that make them up. So here that would be iron ions and chloride ions, and then magnesium ions and chloride ions. And if something doesn't change oxidation state between the left and the right side, then you remove it because it's a spectator ion and it doesn't need to be included in the ionic equation. In the first part of the first required practical, you make a standard solution. This could be in the context of a calculation-based question where you're given a particular volume and concentration and you need to calculate what mass of solute you need. In terms of the method, the first thing we need to do is weigh out the precise amount of solute, and we need to know how much solute has been transferred to the solution, not just what was weighed out initially. So either you do the weighing before and after method, or you're going to rinse everything into the beaker that you're using to dissolve the solute in. Then you dissolve that solute using some distilled water, stirring it with a glass rod to make sure that everything dissolves fully, and then transfer this solution to a volumetric flask using a funnel. You need to make sure you rinse down all of the glassware you're using with distilled water and that all of those rinsings go into the volumetric flask. You then add more distilled water until the meniscus rests on the calibration line, and you may need to use a dropping pipette in order to do that accurately. You then stopper your volumetric flask and invert it several times to homogenise the solution. This inversion has to happen right at the very end. It's not something that you're doing earlier to make things dissolve. Then in the second part, you're carrying out a titration in order to work out the concentration of an unknown substance, and that's what's going in your conical flask. Before you start, you rinse through your burette, but you can't do this with water because that would dilute the solution that you're then going to put in the burette. So instead, you rinse the burette with the solution that will eventually be going into it. If you're putting sodium hydroxide in your burette, you rinse it with sodium hydroxide, and this removes impurities and also allows you to fill up the jet space at the bottom. The substance that you don't know the concentration of goes in the conical flask to allow you to swirl it without it splashing out, and you measure that using a volumetric pipette. That's to make your volume very precise and also to reduce uncertainty. If it's an acid-base titration, you include an indicator like phenolphthalein or methyl orange, and these are good indicators because they have a very clear, distinct colour change. You titrate until you see the first permanent colour change, repeating that process until you get concordant data, which are titers that are within 0.1 centimetre cubed of each other. We often use a white tile underneath the conical flask in order to allow you to see the colour change more clearly. All of your volumes are measured at eye level, looking at where the meniscus lies, and your most accurate data is going to be calculated when your burette contains a very dilute solution, because this is going to mean that the volume that you add is larger and therefore the percentage uncertainty is smaller. You use a wash bottle to rinse down the sides of the conical flask and the outside of the burette to make sure that any solution that leaves the burette ends up in the chemical reaction and not stuck to the sides of the glassware. It's fine for us to do this because when we calculate the final concentration, we're going to use the volume of 25 centimetres cubed that we originally put in the conical flask. We're not going to use the volume that ends up in the flask, so even though you're adding water, you're not changing that starting volume that is what's being used in the calculation. To assess the percentage purity of a solid, we can't use regular titration. So what we need to do is a chemical reaction first before we perform that titration. And this whole process is called back titration. So for instance, if I take solid calcium carbonate and I react that with some acid, before I do that reaction, I can calculate the moles of acid in that acid. And what I then do is I take the leftovers and I use that in a titration with sodium hydroxide to work out how many moles of acid are still in that solution. The difference between those two numbers tells me how much acid has been used up in the initial reaction with the calcium carbonate. In the bonding topic, we discuss 4 types of crystal structure, which is the overall structure of the substance. Is it ionic like sodium chloride, metallic like magnesium, macromolecular, which you would have called giant covalent at GCSE, like diamond and graphite, or is it a simple molecular substance like ice? Unlike at GCSE, where we made distinctions between bonding types based on whether things were metals or non-metals, at A-level we appreciate that it's a bit more nuanced and really we're talking about differences in electronegativity. Elements that have a large difference in electronegativity experience ionic bonding, and this involves electrostatic attraction between oppositely charged ions in a giant ionic lattice. These substances are solid at room temperature because the strong electrostatic force of attraction requires such a huge amount of energy to overcome. It's likely that you may be asked to compare and contrast an ionic substance with a simple molecular substance, and we get that idea that because we've got stronger forces, it takes more energy to overcome them, and therefore we have a higher melting or boiling point. You could also discuss the fact that ionic substances can only conduct electricity when they're molten or aqueous, and the reason for that is that even though they have charged particles, i.e. ions, in a solid they're not free to move. You definitely do not want to be mentioning delocalized electrons anywhere in a question about ionic bonding. You remember from GCSE that a single covalent bond is a single shared pair of electrons, with double and triple bonds existing when multiple pairs of electrons are shared. You also learned in Year 12 that a coordinate or dative covalent bond is one that contains a shared pair of electrons where both of the electrons have been supplied by one atom. For instance, the ammonium ion is produced when an ammonia molecule with a lone pair on the nitrogen is able to donate that lone pair to a proton that it picks up from solution to make the ammonium ion. You might also have encountered dialuminium hexachloride, which is made when one aluminium chloride molecule and another aluminium chloride molecule are joined together by 2 covalent bonds. This is a perfect example of where at GCSE we would have expected a metal and a non-metal to make an ionic bond, but here we actually see covalent bonding. Giant covalent substances contain thousands of atoms. This includes diamond, which makes 4 strong covalent bonds per carbon atom. Remember, there are thousands of these carbon atoms, and therefore melting it is incredibly difficult and needs a lot of energy. Likewise, graphite also contains thousands of atoms, but these are made into hexagonal layers, or planes as we tend to say at A-level, which are able to slide over each other because there are no strong covalent bonds between the layers. Metals consist of a giant metallic lattice, which is made up of regular rows of positive ions and a sea of delocalized electrons. If you're asked to draw this, you should make sure that you're drawing at least 6 ions. There is a strong electrostatic force of attraction between these positive ions and the delocalized electrons. Metals are able to conduct electricity because the electrons that are delocalized are free to move and carry charge through the metal. In a question about properties, the first thing you want to ask yourself is this comparative or is it just about one substance? If you're asked why A has a higher melting point than B, you need to be talking in terms of it having more energy needed to overcome the forces. But if you're just asked why does A have a high melting point, then you need to be saying it takes a lot of energy to overcome those forces. It sounds like a really pernickety thing, but it will cost you marks in the exam. The second thing you want to think about is what are the forces being overcome, which may or may not be the same thing as what type of bonding it has. If it's an ionic substance, then obviously it's a strong electrostatic force of attraction being overcome. But if it's a covalent substance, you need to think, is this a giant covalent structure, in which case the covalent bonds are being broken? Or more likely, are they asking you about a simple molecular substance, in which case it's the weak intermolecular forces that are being overcome? If I have two methane molecules here, and I'm looking at why does methane have such a low boiling point, it's because the weak intermolecular force is being overcome. The strong covalent bonds inside the molecule are not breaking. Then if you're asked about electrical conductivity, you need to think, does this substance have charged particles, and if so, what are they? Please don't write about delocalized electrons if the question asks you about ionic substances. Then secondly, are those charged particles free to move? And this is where we need to think about the fact that ionic substances can't conduct electricity unless they've been melted or dissolved. We can think about electrons as charged clouds that repel each other, and in trying to get as far apart as possible, these can cause molecules to have different shapes. Remember, it's always the electrons that are repelling each other, not the atoms that they're attached to. When you're trying to decide what to call a particular shape, firstly you need to consider all of the electrons regardless of whether they're lone pairs or bonding pairs, and that number of electrons is going to give you your basic shape. And then, particularly for tetrahedral molecules, you're going to need to actually name the shape based on the bonding pairs only. Linear molecules have a bond angle of 180, and watch out because this one often comes up while you have something that you think has lots of extra lone pairs, but when you're naming it, it's just linear because it only has two bonding pairs. Then trigonal planar molecules have a bond angle of 120, and your basic tetrahedral has a bond angle of 109.5. Trigonal pyramidal has two different bond angles. There are two bonding pairs as far apart from each other as they can be at the top and the bottom, and there's a 90-degree angle between them and the three remaining bonding pairs, which form a sort of tutu around the middle, and the angle between them is 120, just like in the trigonal planar molecule. Then we have our octahedral molecule, which confusingly only has 6 bonding pairs of electrons because the name is based on the 8 faces of the 3D shape, and that has bond angles of 90 degrees. Then we should think about our alternative tetrahedral shapes. If we have one lone pair, then this is going to reduce the bond angle by 2.5 degrees, and we call that triangular pyramidal or just pyramidal. And then we also have our bent or non-linear molecules like water, which have 2 lone pairs. So we remove 2 sets of 2.5 degrees to have a bond angle of 104.5. And the reason for that is because the lone pairs are going to repel each other more strongly than the bonding pairs of electrons. To describe differences in intermolecular forces, we need to be able to talk about bond polarity. Electronegativity is the power of an atom to attract the pair of electrons towards it in a covalent bond. I could say that fluorine is more electronegative than chlorine because it has fewer shells, so there's a stronger attraction between the nucleus and the bonding electrons. Remember, it's those bonding electrons, not just generic outer shell electrons like lone pairs. Now, when atoms differ in electronegativity, that will cause the covalent bond between them to become polar, and it's possible that this may lead the whole molecule to be polar if the molecule is not symmetrical. If you look at my diagrams on the right hand side, here I have chloromethane with this one polar bond, and we have a delta negative on the chlorine to show that it's more negative, and that's the more electronegative atom, and the delta positive on the carbon at the other end. Chloromethane experiences permanent dipole interactions between molecules of the same type. But if you look below that at the tetrachloromethane that I've drawn, even though those individual bonds are polar bonds, because the molecule is symmetrical, they cancel each other out, and we don't have a permanent dipole force between the molecules. There are 3 different types of weak intermolecular force, but before we go into them, you need to understand that the strength of these forces have overlapping ranges. It's not the case that every single molecule that has hydrogen bonds between its molecules is going to have a higher boiling point than every single molecule with van der Waals forces. Something with very strong van der Waals forces could have stronger intermolecular forces than something with very weak hydrogen bonds. Say if you consider a really big polymer, it's not polar, it just has van der Waals forces, but because it's so big and has so many electrons, those van der Waals forces are stronger than the hydrogen bonds that we see between water molecules. Our first and strongest type of weak intermolecular force are hydrogen bonds, and there are 2 crucial things you need to understand. The first is a reminder that this is a weak intermolecular force. We mean the force between the molecules, not the covalent bonds inside the molecules. The second thing is that this arises because of the difference in polarity between hydrogen and three key atoms, fluorine, oxygen and nitrogen. So for hydrogen bonding to arise between two molecules, they need to contain bonds that are polar between hydrogen and one of those atoms. It isn't sufficient for a molecule to have fluorine atoms and hydrogen atoms that are not bonded to each other. The second type of weak intermolecular force is the permanent dipole interaction, and this arises when we have a non-symmetrical molecule that contains bonds that are polar, but not as polar as the ones that lead to hydrogen bonding. For instance, if you have carbon bonded to chlorine, that's a polar bond, and if it's a non-symmetrical molecule, that could lead to a permanent dipole interaction between two adjacent molecules. The final type of weak intermolecular force is the van der Waals force, and this arises because of the random distribution of electrons around a molecule. The larger a molecule is, the more electrons it has, and the more likely it is that just by random chance there's an unequal distribution leading to a temporary dipole on one molecule, and this then induces a dipole on an adjacent molecule, and the attraction between the positive end of one molecule and the negative end of the other leads to the van der Waals force. The larger a molecule is, the more likely it is that this arises, and the stronger van der Waals forces that molecule experiences. Endothermic chemical reactions absorb energy from the surroundings and therefore lower the temperature, and exothermic chemical reactions give out energy to the surroundings overall and increase the temperature. Delta H is the symbol used to denote an enthalpy change, which is a heat energy change measured under conditions of constant pressure. If the value of delta H is negative, this tells us that the reaction is exothermic, and if it's positive, then it's endothermic. We measure standard enthalpy changes at 100 kilopascals and a stated temperature, which is usually 298 Kelvin. Standard molar enthalpy of formation is the enthalpy change, or we would accept heat energy change, when 1 mole of a substance is formed from its constituent elements under standard conditions with all reactants and products in their standard states. You need to be saying all reactants and products, not just saying everything. And then standard molar enthalpy of combustion is the enthalpy change when 1 mole of a substance is completely burned in oxygen, or in other words, burned in excess oxygen, and again, all reactants and products are in their standard states. We don't mention standard conditions here because everything's on fire, so it's not standard conditions. To calculate a standard enthalpy from some experimental data, the first step is to work out how much energy is absorbed or more likely released, and to do this we use the formula Q equals mc delta T. Now in this formula, m is mass, but crucially it's the mass of whatever is changing temperature. If you're doing some flame calorimetry, you're burning a fuel and you're heating up some water, so it's the mass of the water, not the mass of the fuel. Then C is the specific heat capacity, which you're going to be given in the question, and T is the temperature. And because it's a change in temperature, it doesn't matter if that is measured in degrees C or in Kelvin. For the second required practical, you measure an enthalpy change, and the one that is recommended is dissolving copper sulfate. We do this in a polystyrene cup in order to minimise energy losses to the environment. And before you start, it's really important that you take the temperature at regular intervals for a long enough time, usually 4 or 5 minutes, and this is to establish an accurate starting temperature and to make sure that the temperature of the water wasn't changing before you did anything to it. Then we need to dissolve the copper sulfate in the water, and it's important here that we have to use the weighing before and after method. You can't use the rinsing method because in order for us to calculate an accurate enthalpy change, we need to have a known mass of water and it all needs to be interacting at the same time, so you can't use rinsing. Weigh the weighing boat with your copper sulfate in and then pour it out, and weigh that weighing boat afterwards to see how much copper sulfate was transferred, because there may be residue. Measure the temperature over several minutes, maybe up to 15 minutes, and then plot the temperature against the time, and you're going to draw 2 lines of best fit. One for your initial readings, where it's just the water, and then one after you added the copper sulfate. You then extrapolate both of those lines of best fit back to the point where you added the copper sulfate, and the difference between them is the temperature change. You can use that information together with Q equals mc delta T to calculate the overall energy change. We're then going to convert that number, which is in joules, to kilojoules by dividing it by 1,000. And what we're then going to use the mass of the copper sulfate for, as opposed to the mass of the water, is to work out how many moles of copper sulfate were added so that we can work out an enthalpy change per mole. So you take Q, which you've converted into kilojoules, and you divide it by the number of moles, and that's your delta H value. Hess's law tells us that the enthalpy change for a reaction is independent of the route taken. Questions may ask you to work out an overall enthalpy change, or give you that overall enthalpy change and ask you to work backwards from that to work out one of the intermediate steps. I would always draw a Hess's cycle because it's much easier to pick up working marks for a cycle than it is for a mathematical expression. The first thing you need to do is look at your table of enthalpy change data and decide is each one combustion or formation data, and then write an equation for each one of these processes. Now that I've got these expressions, it's much easier for me to draw my cycle because they tell me which way my arrows need to go. Here I'm going to be making carbon dioxide, and I can add in my 2 arrows, and I know which way they're going because I can see from the equations I've already written. Then I can add numbers onto those arrows, and I need to watch out for the fact that although in this instance I've only got 1 of each, if I have multiple moles of a particular substance I may need to multiply up those values. Then I'm going to write start and end on either end of the arrow that I'm going to try and work out the value of, and draw a new arrow that goes from start to end but going the whole way round the rest of the cycle. This is going to help me see, am I going the right way up arrows or the wrong way up arrows? Here I'm going the right way down the -393 arrow, so I keep that number as it is, but I'm going the wrong way up the -283 arrow, so therefore I need to flip the sign or just add another minus, and I can work out that the overall enthalpy change for this reaction is -110 kilojoules per mole. When we define mean bond enthalpy, this is the amount of energy required to break 1 mole of the stated bond because it's a standard enthalpy change. But this is also averaged across a range of compounds that contain that bond because there isn't one gold standard value for how much energy it takes to break a carbon-oxygen bond. It depends upon the context of the rest of the molecule. This leads to differences between experimental data for one compound and the databook. You may be working out the energy change for a reaction based upon some bond enthalpy data. We need to add up all of the bonds that are going to be broken and subtract from that all of the bonds that are going to be made, and the difference between those two numbers is the overall enthalpy change. If it's negative, this shows you that the reaction is exothermic, and if it's positive, then it's endothermic. It's much more common that you'll have a situation where you're told what the overall enthalpy change is, and you need to work backwards to figure out the value of a particular bond. If you do a quick sketch of the different molecules, this allows you to cross out the bonds as you include them, and it saves you from forgetting to include a coefficient. Here we write an expression for all the bonds on the left, take away all the bonds on the right. If you've got a reaction where not all the bonds actually need breaking, then it's up to you whether or not to include these ones. Both versions will be in the mark scheme. Once we've written out this expression, we can start to simplify it. Make sure that you've got extra brackets around everything on the right hand side because very commonly people will take away that first set of bonds and not the 4x. Then we can simplify this down further, and one thing that's worth pointing out is that the final mark of this calculation is for finding out one of the bond. So even if you have a complete brain melt and you can't remember how to get through the rest of the calculation, if you've done something that involves all of the numbers that you've been given and then you divide by the appropriate number, you can still pick up a mark there. Since kinetics isn't included in paper 1, we move straight on to equilibrium and the Chatelier's principle. This applies to reversible reactions, which you can identify because they contain the reversible reaction arrow. At equilibrium, the forward and reverse reactions proceed at equal rates, and this means that the concentration of the reactants and the products remains constant. It does not mean that they are the same as each other. We can use Le Chatelier's principle to make predictions about the impact of changing temperature, pressure, or concentration. In the first line of your answer, say that the system will shift to counteract the change. Although unlike at GCSE, where that statement on its own would be enough, you need to make sure that you include what the change is. For instance, saying the system shifts to counteract the increase in temperature. Next, include which reaction is being favoured and why that's the case. For instance, we might favour the endothermic reaction because we're trying to reduce the temperature after a temperature increase. Or it might be that the side with fewer molecules is favoured because we're trying to reduce the pressure after it's been increased. Thirdly, specify which side the equilibrium moves to. If you're favouring the forward reaction, it's moving right, and if the reverse reaction is favoured, equilibrium is moving left. Finally, describe what the impact on the yield will be. Remember, adding a catalyst does not affect the position of equilibrium or how much product you make. The reason for this is that the forward and backwards reactions are both going to be sped up by the same amount. The reaction will reach equilibrium sooner, but the overall concentration of the product will be the same. You need to be able to write a Kc expression for systems where everything is in the same phase, so either everything is a gas or everything is a solution. The first thing you need to be able to do is write an expression for Kc. We're using concentration, which we show using square brackets. The products go on the top of the expression and the reactants are the denominator, and the coefficients in the symbol equation are going to become the powers in that expression. In order to work out the units, we start from the base unit of moles per decimeter cubed because all the concentrations are measured in that. You could choose to write it out for every single thing in the expression and then cancel them out, or you can look at your symbol equation. So here we've gone from 4 moles on the left to 3 on the right, so we've had a decrease of -1. So if we put moles per decimeter cubed to the power of -1 and we solve that, then we eventually get the right units. One mistake that we regularly see from students in equilibrium questions is that they put numbers into this Kc expression that are not actually concentrations. So you've usually already worked out the number of moles of something, and you need to turn that into a concentration by dividing it by a volume. Often, before we can substitute concentrations into a Kc expression, we're going to need to work out the number of moles at equilibrium. So we'll be given something like this, where we're told the starting moles of two of the substances and also the end moles of one thing. So the easiest way to get around this is to draw what I call an ice table. So you're going to think about the initial moles and also what you've got at the end. So if I look at A, I can see that A has decreased by 0.3. And then I can use the coefficients in the equation to tell me how much everything else has changed by. And that will allow me to work out the final moles of all of the different substances. I then need to take that data and go on to calculate concentration for each one. We then move on to redox reactions, and you know from GCSE that oil rig exists, so oxidation is loss of electrons and reduction is gain of electrons. But in year 12 we learnt that oxidising agents oxidise other species by accepting their electrons, and reducing agents reduce other species by donating their electrons. Oxidation states are a numerical way of representing how electrons move within redox reactions. To work out the oxidation state of any element, there are a certain number of rules that you need to have memorised. The first one is that elements always have an oxidation state of 0. From that point onwards, the rule is that if two rules contradict each other, you always go with the most electronegative element. So first up, fluorine. Fluorine is always an oxidation state of -1 in a compound. Oxygen is -2 unless it's either bonded to fluorine, in which case that rule takes precedence, or if it's in a peroxide where it has an oxidation state of -1. Chlorine has an oxidation state of -1 unless it's bonded to something more electronegative, so in which case that rule takes precedence. Hydrogen is +1 unless it's in a metal hydride, in which case it's -1, and group 1 metals are always +1. Unlike in a simple equation or an ionic equation, for a half equation we're only interested in one particular element, although we are going to have to include hydrogen and oxygen to make it work out. Your first step is to identify which element is changing oxidation states and make sure that element is balanced. In this example, the manganese is already balanced, but particularly if you're working with non-metals, you may have a situation like this chloride ion discharging where you need to add a coefficient in order to make these things work out. Next, I'm going to add water molecules in order to balance out the oxygen that I can see on the left-hand side, and then I'm going to balance out these 8 hydrogens I've just added by 8 hydrogen ions on the left. Now I need to add electrons, so I've got a 2+ charge on the right hand side, and on my left hand side I've got a minus and 8 pluses, so that gives me +7, so therefore I need to add 5 electrons. You may also have been taught to do this by looking at the oxidation states, so we could say that on the left here we've got +7 and on the right we've got +2, so that will need to be balanced out by those 5 electrons. If you're going to combine two half equations, you need to have the same number of electrons overall. Here I've got 5 on my left hand side and 2 on my right hand side. So the lowest common multiple of those would be 10. And so I'm going to take this first equation and times it by 2, and the second equation and times it by 5. So now I'm able to cancel out the electrons, but I'm also able to cancel out some of the hydrogen ions. So I can replace that one there with 6 hydrogen ions that haven't been cancelled out. And now I'm just going to join these two equations together to produce an overall equation that looks like this. In the first topic of inorganic chemistry, we learned that elements can be classified as belonging to the S block, the P block, the D block, or the F block, based on where they're found in the periodic table. And this in turn is determined by their proton number and which subshell their highest energy electrons are found in. Next, we look at some general trends across the periodic table, using period 3 as our model for it. So the first trend is that as we go left to right across the period, the atomic radius decreases. And the reason for this is that we're increasing the number of protons and therefore the nuclear charge. And this means that the strong electrostatic force of attraction between the nucleus and the outer shell electrons gets stronger. There aren't any more shells, everything in period 3 has 3 shells, so we're not having any increase in shielding, so it's just the nuclear charge that is affecting the radius. Even though we've already discussed first ionization energy, I'm going to take the opportunity to remind you again that these state symbols are crucial and you won't get the mark without them. You need to be able to describe that as we go left to right across the table, the first ionization energy in general gets higher because of the increased number of protons, with a couple of key exceptions. Firstly, when we get to aluminium, our highest energy electron is in the 3p subshell, which is higher energy than 3s, so we see a small dip, and then we see another dip when we get to sulfur, because here we have electrons being paired, and they are going to repel each other more than the other electrons already were, and so therefore it's going to be easier to remove that first electron. In order to describe differences in melting point across period 3, we need to think about what kind of crystal structure we have. So sodium, magnesium and aluminium are all examples of metallic structures, where silicon is giant covalent, and then phosphorus, sulfur and chlorine are simple molecules, and argon of course is monatomic. The second question to ask yourself is, what is the force that's being overcome in order for this substance to melt? So for the metallic substances, it's a strong electrostatic force of attraction between the positive ions and the delocalized electrons. For the giant covalent structure, it's covalent bonds. And for the simple molecular substances and also the monatomic noble gas, it's going to be van der Waals forces. You could be asked to compare two substances from two different categories, say a metallic one and a simple molecular one, but you could also be asked to make comparisons within a category. So for instance, we can say that magnesium has got a higher melting point than sodium because it's got higher charged ions and also it's got more free electrons to make that bond. Likewise, if we look at our simple molecular substances, we know that phosphorus makes a P4 molecule, sulfur makes an S8 molecule, and chlorine makes a Cl2 molecule. And this is reflected in their melting points as well, because those molecules have more or fewer electrons and therefore stronger or weaker van der Waals forces. The alkaline earth metals are found in group 2 of the periodic table, which is part of the S block. They have 2 electrons in their outer shells and therefore they make 2+ ions, which is important for you to remember when you're creating symbol equations involving them. Because they're metals, they conduct electricity and they conduct heat. As you go down group 2 from beryllium to barium, the atomic radius gets larger. This is because the impact of adding another electron shell is much greater than the impact of the additional nuclear charge from the extra protons. Linked with this is the trend in first ionization energy. As you go down the group, the energy required to remove the first electron decreases, because the ions are getting bigger, and this means that there's a weaker force of attraction between that outer shell electron and the nucleus. The melting point also decreases as you go down the group, from about 1300 for beryllium down to about 700 for barium. Again, this links back to atomic radius. The atoms or cations are getting bigger, but there isn't any change in overall charge. They're all 2+ charge ions. And so that means that that charge is kind of more spread out. And so this means that overall the charge density decreases, and therefore the strength of the attraction from the ion to the electrons also decreases. As with all metals, the group 2 metals get more reactive as you go down the group, because the outer shell electrons are more easily lost because they're further from the nucleus and they experience more shielding due to the greater number of shells. You need to be able to write equations for the reactions of group 2 with water, and in the case of magnesium there are different equations for steam and for liquid water. So for steam, we're going to have our solid magnesium with our gaseous water, because it's steam, reacting to make magnesium oxide and hydrogen, and you're going to observe a bright white light, just as you do if you make magnesium oxide by putting magnesium in a Bunsen burner. Then when magnesium, calcium, strontium and barium react with liquid water, it's acting as an oxidizing agent. So the magnesium is going to react with liquid water to make magnesium hydroxide and also hydrogen gas. That magnesium hydroxide would be a solid because magnesium hydroxide is sparingly soluble, so it's not really going to go into the solution. We know it's a tiny bit soluble because the pH is going to change by a tiny amount, but not by nearly as much as we would see if we had, say, calcium hydroxide, which is soluble and therefore would have the state symbol AQ. Calcium hydroxide is a colourless solution, but you are also going to be able to see some bubbles or effervescence from the hydrogen gas. The group 2 hydroxides get more soluble as you go down the group, and we can identify this by looking at the impact on pH. As we've just mentioned, magnesium hydroxide is only sparingly soluble, so a solution of magnesium hydroxide might only have a pH of 8 or 9, compared to a solution of barium hydroxide, which could be as high as 13 or 14. In terms of their uses, magnesium hydroxide is put in indigestion tablets in order to neutralise excess stomach acid, and calcium hydroxide is used by farmers to neutralise acidic soils in the fields where they're growing crops. Now, in contrast to the hydroxides, sulfates get more soluble as you go up the group. So the one to remember is barium sulfate, which is used in barium meals. In other words, it's used as a radiographic contrast agent. So if you're trying to take an X-ray of someone's intestines, they eat the barium meal, and the barium sulfate will reflect their X-rays in the same way that bone would. It's safe to do this even though barium sulfate is incredibly toxic, because it won't dissolve in the body's fluids and therefore it can't be taken in. Barium chloride is also used as a test for sulfate ions. So the barium ions from the barium chloride will combine together with any sulfate ions that are in a solution to make a white barium sulfate precipitate. When we do this test, we acidify it first, usually using hydrochloric acid, because that way we're only adding chloride ions, which are in the barium chloride anyway. And the reason we do that is to remove any carbonate ions, which would give a false positive in that they would also generate a white precipitate. Titanium is a really important metal because it's so lightweight, and so it's used for things like making jet planes. In order to extract it, we take an ore called rutile and heat this with chlorine and coke to turn titanium oxide into titanium chloride. And then the titanium chloride can be further reduced using magnesium, or in fact sodium, as a reducing agent, in other words, an electron donor. So you should be able to write symbol equations for that process as well. Sulfur dioxide, which is responsible for sulfurous acid, which causes acid rain, can be removed from waste gases from a power station by an acid-base reaction with calcium oxide. Basically, we spray a slurry into the gases that contains these calcium-based compounds, and this removes the sulfur. Finally, we have the halogens, which are found in group 7 in the P block and all have 7 valence electrons. Just like group 2, as we go down the group, we're going to see that there is an increased atomic radius because we're adding a new shell each time. Electronegativity is the tendency or power of an atom to attract a pair of electrons in a covalent bond towards itself, and fluorine is the most electronegative element in the whole periodic table, with electronegativity then decreasing as we go down the group. This also means that as we go down the group, things become steadily less good oxidizing agents, so fluorine is a very good one, astatine is a much poorer one. The reason for all this is this larger atomic radius, including more shells. So this means that the outer shell electrons are experiencing more shielding, and therefore there's a decreased attraction between the nucleus and the bonding electrons. And this is really important. You need to be talking about the bonding electrons, not just outer shell electrons in general, because electronegativity is about attracting electrons that are in a covalent bond. This also means that the bond polarity decreases as you go down the group, so we know that when fluorine bonds, it makes very polar bonds often, and also this is going to mean that the bond strength also changes. In terms of the boiling points, we know that fluorine and chlorine are gases, where bromine is a liquid and iodine is a solid. And so all of these small covalent molecules are experiencing van der Waals forces. But because bromine and iodine are larger atoms and they make larger molecules that have more electrons, the van der Waals forces are stronger. This means that they take more energy to overcome, and therefore iodine is going to have a higher boiling point than bromine, and bromine higher than chlorine, and so on. The more reactive higher up halogens are able to displace the less reactive lower down halogens from their compounds. So for instance, chlorine in the form of chlorine water can displace bromine from potassium bromide. Chlorine water is a very, very pale green, almost colourless, and in this reaction we would see an orange solution forming as the bromine water formed. If we repeated this process with potassium iodide instead, we'd see a darker brown solution forming. You also need to be able to write ionic equations for this, in which case we would remove the spectator ions and just not include the potassium. And you also need to be able to write half equations too. When sulfuric acid reacts with solid sodium halides, it can perform two different roles. Firstly, it acts as a proton donor or an acid. So if we have some sodium chloride reacting with sulfuric acid, we make steamy white fumes of hydrogen chloride and also some sodium hydrogen sulfate. And this process will happen for any of the halides, and they're all just functioning as bases. But then if we think about bromide ions and iodide ions, which are the best reducing agents, then the reaction is able to go a little bit further with the acid acting as an oxidizing agent. This won't work for fluoride ions or chloride ions because they're not powerful enough reducing agents. So if we take hydrogen bromide that was formed in the first reaction, this can be split up into hydrogen ions and bromide ions, and these can react further with the sulfuric acid to make some bromine and some sulfur dioxide and some water. And you can see here that the sulfur is moving from a +6 oxidation state to a +4 oxidation state, so it's being reduced and acting as an oxidizing agent. Now in this process we make this sulfur dioxide, which we can't see, but because the bromine is produced at the same time, this makes the fumes turn brown. And then if we think about the iodide ions, we have a slightly different process. So we have these 8 electrons here, they're coming from the iodide ions, 8 of them being oxidized to produce 4 iodine molecules and also these 8 electrons. And this can happen because iodide ions are an even stronger reducing agent than the bromide ions. You can test for the presence of halide ions in solution by using acidified silver nitrate solution. We acidify using nitric acid to begin with because this will remove any carbonate ions from solution, and these would lead to a false positive because they would also give you a white precipitate. When you add the silver nitrate, silver fluoride would be produced if you had fluoride ions, but this is soluble, so there isn't an observable change. Whereas silver chloride will produce a white precipitate, and you should be able to write an ionic equation for this, showing how the two soluble ions form together to make this insoluble precipitate. So silver chloride is a white precipitate, silver bromide is cream, and silver iodide is yellow. And if we wanted to analyse those further, say look at how much was made, we could filter them out of the solution because they are insoluble. Now, if you produce just silver chloride or silver bromide in isolation and you don't have anything to compare them to, it might be hard to say whether it is white or cream. So we can identify this further by adding dilute ammonia, because silver chloride will redissolve in that dilute ammonia, but silver bromide will not. Small, carefully controlled amounts of chlorine are added to both drinking water and swimming pools in order to kill harmful microorganisms, despite the fact that chlorine is toxic. This is because, on balance, the health benefits about not having pathogens in that water outweigh the risks of adding a small amount of a toxic substance. Chlorine can react with water in two different ways, depending on whether sunlight is available or not. When there's no sunlight, we see the chlorine reacting with water to make two different acids, hydrochloric acid and chloric acid. This is described as a disproportionation reaction because the chlorine is both reduced and oxidised, going from an oxidation state of 0 in chlorine to -1 in hydrochloric acid and +1 in chloric acid. And we can describe these processes using half equations. In the presence of sunlight, we see a different reaction being undergone, and as well as hydrochloric acid, we also have the production of oxygen gas. When chlorine reacts with cold dilute aqueous sodium hydroxide, it produces two major products, sodium chloride and sodium chlorate. Going from the oxidation state of 0 in the elemental chlorine, in the sodium chloride, the oxidation state of chlorine is -1, and in chlorate, it's +1. So this is another example of a disproportionation reaction. This is sometimes referred to as sodium chlorate 1 to differentiate it from sodium chlorate 5, which we'll get to in just a second. So we have two major products here, and the sodium chlorate can be used for a variety of things, including making herbicides, explosives, dyes, cosmetics, pharmaceuticals, and paper. Then if the sodium hydroxide is hot, we have a different reaction going on, but this one is still a disproportionation reaction. So this time we have sodium chlorate 5, where the chlorine has an oxidation state of +5 instead. And then the very last thing in paper 1 of AQA AS Chemistry is the fourth required practical, which is a series of test tube reactions to identify cations and anions. Now we've gone through most of this already, but just to recap, we can identify which group 2 ion is present by looking at the solubility of their hydroxides and their sulfates. So if we add sulfuric acid, we're going to make a group 2 sulfate, and whereas barium sulfate is highly insoluble and forms a white precipitate, magnesium sulfate is very soluble, and so we would just see a colourless solution. If we think we might have ammonium ions, then we add sodium hydroxide and warm in a water bath so that ammonia gas would be given off. And then we test those fumes to see if they are ammonia gas with damp red litmus paper, which will turn blue in the presence of ammonia. As we've said, to identify group 7, we use acidified silver nitrate, which will form a white precipitate for chloride ions, a cream precipitate for bromide ions, and a yellow precipitate for iodide ions. And we can then also try to dissolve those precipitates using dilute ammonia, and the silver chloride precipitate will dissolve, but bromide wouldn't dissolve. If we think we might have hydroxide ions, of course, those are what are found in alkalis, so we can do some kind of pH test, usually red litmus paper, which would turn blue. To test for carbonates, we can add any dilute acid and we would see effervescence, and if we really wanted to be sure, we could test that effervescence with lime water, which would turn cloudy if it was carbon dioxide being given off. And finally, to test for sulfate ions, we use acidified barium chloride, which will form a white precipitate. Thank you for watching, and I hope you're now feeling a bit more prepared for AQA AS Chemistry Paper 1. Good luck for your exams, and if there are particular topics you'd like me to go over in more detail, let me know in the comments below.